Right, guys, good morning. So, we are starting the new lesson, and for the people online, the tutors are sent. And, if you have received it or haven't received it, you will be receiving soon. For now, just use the the recording if you have any of the issues, right? Right. So the first topic, now we are combining two of the lessons. One is thermodynamics, that is about the thermochemistry. The other thing is kinetics, that is about the rate of reaction, right? And the thermal chemistry or the thermodynamics is about the heat of reaction, right? So now this is the thing, you have to think a little. Now listen, right? So you have to think a little. So in the previous lesson we discussed what was heat. Yes, we discussed what was heat and what we can do with the heat. Yes, we discussed, right? And how to calculate the heat and everything. So how do you calculate the heat? mc theta, that is the equation, right? We use mc theta to calculate the heat. And did you ever thought, how and where did this heat came, right? How and where the heat came from? Did you ever thought of it? If you know it, better be silent. So what was your answer? Yeah. No, not that. You can not that one. Now let's think something like this. If you are using petrol or something, right? So you are using petrol to run a vehicle. Let's say a car or something, right? So the energy that it needs to run the car is completely given by the combustion of petrol, isn't it? So now a heavy vehicle runs with the energy of petrol. Have you ever touched petrol or something? Yes, you have, right? So did you ever think that petrol has this much of energy inside it? No, right? So where did this energy came from? The petrol had that much of energy inside of it. Yes, the petrol had that much of energy inside of it, and we took it out. How? By reacting it with oxygen. That is a combustion, isn't it? You reacted the petrol with oxygen, and that is a combustion, and with the combustion the energy was released, wasn't it? The energy was released, sort of an energy that was containing inside the petrol came out, right? Containing inside the petrol came out with the reaction, right? And we call that the internal energy of the petrol, and the heat that came out, or the energy that came out, we call it the heat of reaction, right? We call it the heat of reaction, right? The heat of reaction, do you understand now? It came inside from the petrol, wasn't it? It came inside from the petrol. So the petrol has energy, right? Petrol has energy, and when it reacts, the internal energy of that petrol, what happens? Comes out. So now in this lesson, what we discuss is that internal energy, right? How do we calculate that internal energy? How do you find the internal energy of an substance? Yeah, that is what we discuss. ආවම් පස්සේ ටික. ඔව්. අපි හීට් එකේදී කතා කරේ හීට් එක එළියට ආවම් පස්සේ මොනවද කරන්න පුළුවන් කියන එක. දැන් අපි මේ ලෙසන් එකේදී කතා කරන්නේ ඒ ඇතුලේ තියෙන හීට් එක කැල්කියුලේට් කරන්නේ කොහොමද කියන එක. get it? කියන්නේ මොකක්ද තියෙන ඉන්ටර්නල් එනර්ජි එක කැල්කියුලේට් කරන්නේ කොහොමද කියන එක තමයි ඩිස්කස් කරන්නේ. Right? So we are discussing about the internal energy, that when the petrol combusted, sort of a energy is released to the outer environment, and that energy can drive a car, yeah, and that energy gives the driving force to a vehicle, and that's a huge energy, isn't it? That's a huge energy. But if you took a bit of a petrol, the petrol doesn't seem to have that much of a energy, isn't it? The teeny tiny the people have sort of energy that you don't see it, right? That's inside of him, and that is called the internal energy. So they are in this lesson. What we do is we are going to measure that internal energy. Get it? We are going to measure that internal energy, and there is one sort of a way the energy is released in the reaction, right? In the petrol, in the combustion, energy is released. Is it always releasing energy? No. In some cases, the energy is absorbed as well, right? Like in the probably next week, I'll show you one of the acid and base reactions, and I'll give the setup to experience for you as well, like how the heat is released. You will feel it. Now for today, I brought a glass of water from Vice Path Education and a glucose from the pharmacy next to Vice Path. So I brought a glucose. Now if you dissolve glucose in water, have you ever dissolved glucose in water? Yeah, in the school? Yes. So what happens when you dissolve glucose in the water? Oh dear, we know that's true. We all know that. How do you feel about the heat? It makes a like a cool sense. Yes, it makes a cool sense, doesn't it? So why does it feels like cool? What happens there? When the reaction occurs, what happens? The energy is absorbed. Yet, so the energy is absorbed. Because of that, the energy is took from the environment. So the environment feels cool. So that means in the reaction they have absorbed energy, right? So now few of the things can happen. I will write this down, right? Now few of the things can happen. Listen. So now few of the things, something like this can happen, right? Let's say A plus B, right, are reacting to produce C, right? A plus B are reacting to produce C. Let's say C plus D. We have another product because the reactants have two of the A and B, and the products have C and D. So these are the reactants, these are the products. Yes. So now let's say the reactants had a 15 joules of energy inside of it. This is inside energy, not outside energy, right? This only remains inside. You can't measure it with the kinetic energy or anything like that, right? It's inside of it, you can't measure it, right? So you have to take it out to measure. That is how you measure it. You have to take it out somehow. So the internal energy of the two of the reactants is 15 joules together. And when the reaction occurs, sort of energy is released. So the product's energy is 10 joules, right? Now the product's energy is 10 joules. So how much has released? 5 joules is released, right? 5 joules has released as energy. Yes. So we call this which kind of a reaction? We call this a exothermic reaction, which means the heat is released, right? We call this an exothermic reaction which the heat has released. So where did the heat release from? From the internal energy of the A plus B. Can this be seen when the A plus B is there? No, you can't see it. It was inside of it. Yes. So it was released as 5 joules. Yes. And there could be another reaction, like let's say X plus Y reacts to produce E plus F, right? And the internal energy of X plus Y is 10 joules, right? And when they react, the products formed has an energy of 15 joules, right? The products has a 15 joules of energy, right? So now what has happened when the reactants react? the energy has absorbed. Yes, the energy has absorbed. So where does the energy is absorbed from? It's from the environment. They took the energy from the environment. And where does this release to? It is same to the environment, right? So now in this case, this is 5 joules, this is 15 joules, means minus 5 joules, right? Minus 5 joules is there. Minus 5 joules means like the energy is absorbed. Oh, like the better I will write it here. So 5 joules is taken from the environment when the reaction occurs and is converted into products, right? Oh, ඒ කියන්නේ අපි සාමාන්‍ය මෙහෙම ලියන්නේ මේ කියන්නේ මේකේ අපි මෙහෙම එනර්ජි එක රිලීස් වෙනවා ඇඩ් වෙනවා කියලා දදා ලියන්නේ. ඒ කියන්නේ question එකට එනකොට මීට වඩා අපි different format. This is just the theory. I'm trying to explain the theory, right? So මේකේ එතකොට exothermic එකක් මේකට අපි කියන මොකක් කියලාද? We call this a endothermic reaction. In an endothermic reaction, what happens? The energy is absorbed. So there are two types of reactions. One is exothermic, which releases the energy, and the other thing is endothermic reaction, which absorbs the energy. So now in a exothermic reactions, the reactants has higher energy and the products has low energy, because the energy, the higher energy which had in the reactants was released to produce the products. That is why the reactants has a greater energy and the products has a low energy. Yes, in a exothermic reaction, exothermic එකේ හැමතිස්සෙම reactants වල energy එක වැඩි, products වල energy එක අඩුයි. ඇයි? එයා energy එක release කළා තමයි products හදන්නේ. නේ? මෙයාගෙන්මනේ මෙයාව හැදෙන්නේ. So it releases energy to produce the products. So the energy in the products is less, energy in the reactants is higher. Understood it? Yes? People online understood it? So in an exothermic reaction, the energy of the reactant is higher and the energy of the product is lower. Get it? And in an endothermic reaction, what happens? They absorb energy to produce products. So in the reactants, the energy is low, but when it produces the products, the energy is high, right? So if it is an exothermic reaction, the energy of reactant is high, energy of product is low. If it is an endothermic reaction, energy of reactant is low, energy of product is high. Now remember it this way, like relatively to the reactants. If the energy is more, released. If the energy is less, absorbed. Relatively to the reactants. Reactants වලට relatively මතක තියාගන්න. If the energy is more, release. ඒ කියන්නේ reactants වල energy එක more නම් release. Reactants වල energy එක less නම් absorb. එහෙම මතක තියාගන්න. If the energy is more, released. Energy is less, absorbed. Right? The reactants වලින් මතක තියාගන්න. Right? So two of the reactions are there, exothermic and endothermic. Right? So in these two of equations, if we measure or calculate the heat of reaction, this is how you do it. Right? Heat of reaction එක කියන්නේ simplest way එක. මේකට වඩා අපි advanced විදිහකට අපි ඉස්සරහට කතා කරනවා. Simply, if you want to calculate the heat released or absorbed by the reaction, this is what you do. Right? Heat of reaction, right? Heat of reaction is taken this way. The energy of what? Energy of products, right? Energy of products minus energy of what? Reactants, right? This is how you calculate the heat of a reaction. Energy of products minus energy of reactants. Always product minus reactants, product minus reactants, right? So if it is an exothermic reaction, now tell me the values. First one is an exothermic reaction, isn't it? So the energy of the product is how much? 10 joules, and the energy of the reactant is 15 joules. So minus 15 joules, and gives an answer of how much? Minus 5 joules, isn't it? So if the heat of reaction is minus, that means what? It's a exothermic reaction. That is one of the points to remember, right? If in any of the questions, if you got a minus energy, that is a exothermic reaction, isn't it? That is a point to remember. If it is a minus energy, that's the exothermic reaction. Yes. And if I take the second one, tell me the values. Now the same equation, nah? So I'm not going to write it again. I'll write it like different color. Now this. So what is the energy of the reactants in the second reaction? Energy of the products is 15 joules minus energy of the reactants is 10 joules, and deducting you get how much? Plus 5 joules. So if the heat of reaction is plus, that is a endothermic reaction, right? That is a endothermic reaction. That is enough for now, right? Did you understand up to that? Yes. There are two of the equations, exothermic and endothermic, and that exothermic or endothermic is always the energy is either absorbed to the internal energy or released from the internal energy, and you can't measure it from the outside, right? You can't measure it like you can't measure the energy of that petrol from the outside, because it's internal energy that is contained inside of it, right? In a different way. In the how do you think the internal energy is stored there? How do you think the internal energy is stored there in the petrol? Yeah, sort of kinetic and potential energy is the energy that is there. The energy that it contains inside the molecule is because of the attractive and repulsive forces of electrons and protons. The energy inside the molecule is because of the attractive and repulsive forces of the electrons and protons. Get it? That is the internal energy. You can't see it outside. It's there. You can see it when it's unstable, right? You can see it unstable. It's something like this. Now I'm trying to explain this for the knowledge. Now something like this. Let's say Penuja, Johan and Ravishka are holding hands like this, right? So three of you are like holding your hands like this. This is the molecule. So three of you makes one molecule, right? This is just a theory, right? So three of you are making a molecule. So this is three of you, right? So you are one molecule, and you are like grabbing to three of the sides, pulling three of the side. But since it's under an equilibrium, since the forces are equal, it doesn't move, but the energy is still there. And let's say Johansa comes and tickles Johan or something, right? That means a bit of a instability is given. See likewise, right? So Johansa comes and tickles Johan. What happens to the stability inside of the molecule? It breaks. Now what happens? Energy is released. Energy is released, right? Because now our කලින් stability එක නැහැනේ. එතකොට ඒගොල්ලෝ movement එක වෙනස් වෙනවා. movement එක වෙනස් වෙලා ඒගොල්ලන්ගේ energy එක වෙනස් වෙනවා, break වෙනවා. Sometimes in that case the bonds can break, නේ? Because of that, let's say Ravishka's was නේද thrown away, right? දැන් මෙයාව යොහාසා පොඩ්ඩක් ඇවිල්ලා ටිකල් කරනවා. So because of that, the stability was broken. So now Ravishka was thrown away. So now Penuja and Johanna are holding the hands. Now what happens to the Ravishka? He is now thrown away. Now it's two different energies, and it's not equal to the complete energy of this as well. Bit of energy is released. Maybe Yohasa took it. Let's say Yohasa was the environment. So someone took it. Usually the energy was taken from by the environment, right? So now let's say this had 30 joules, and Johan and Penuja together has a 20 joules, and Ravishka has 5 joules. Now 5 joules has released to the environment, and that is exothermic reaction. How it happens actually in internal, as in internal energy, right? So simple, like in a nutshell, it's something like this, right? Right. So that is for the knowledge, huh? Right. So shall we come to the theory back? Right. Internal energy of a system. The sum of kinetic energy and the potential energy of the particles in a system is called the internal energy of the system. That means the attractive and repulsive forces of electrons and protons, right? And let's say this is one of the reactions, a combustion reaction of methane and oxygen. Methane is the biogas, reacts with oxygen to produce carbon dioxide and H2O, plus energy is released, right? Energy is released. Now let's say the methane had 5 joules of energy, sorry, let's say 10 joules of energy, right? Now only water molecule and carbon dioxide together has 5 joules of energy, right? It's written there, 5 joules of energy, right? Methane and oxygen had a 10 joules of energy, and the carbon dioxide water has a 5 joules of energy. Now what happened to the other 5? That is the energy release, and that's a exothermic reaction, right? That's the exothermic reaction, right? Can you feel it? So this is, if I take it 10 joules, if this is 5 joules, the 5 joules of energy is released, and it's a exothermic reaction, right? It's an exothermic reaction. What happened? Yeah? Exothermic reaction happened. Right? So it is believed that balance of the attractive and repulsive forces caused by the electrons and protons present in the molecules create internal energy, right? In a reaction, the rearrangement of these attractive and repulsive forces changes, so the internal energy of the resulting molecules increase or decrease compared to the reactants. That is what happens. Understand this part? Yes? Our rearrangement එකත් එක්ක සමහරකට energy එක release වෙලා තියෙන නැත්නම් energy එක absorb වෙලා තියෙන, right? So the heat of reaction is equal to energy of the product minus energy of the reactants. So in the above case, delta H2 was the energy of the product, that was 5 joules. That was 5 joules. And the energy of the reactants, delta H1, was 10 joules. And the answer is what? Minus 5 joules. And this is the heat of reaction. So the heat of reaction is how much? Minus 5 joules. Minus 5 joules. And the minus means energy is depleted or released. Yes? Minus means the energy is depleted or released. Thrown away. The energy is left. Yeah, the energy left. The energy left the reactants makes the exothermic reaction, right? Right. Understood up to this? Yeah. People online, if you have like any of the questions, right, you ask. These, these theories, it's good. It's a good thing. Yeah, it's a good thing you question it, because more you question, more you understand, and be logical with the questions. Be logical with the questions, and it's a good thing to ask, right? If you have any of the doubts, how it happens, why it happens, right? Ask anytime, right? So come to this topic, heat of reaction, exothermic, right? Please. Yes. ඒක ඇත්තටම අනිත් පැත්ත වෙන්නේ. කියන්නේ bonds break වෙනකොට energy එක absorb වෙනවා. කියන්නේ bonds break කරන energy එක ඕනනේ. bonds හදනකොට energy එක release වෙනවා. Yes. Like remember it this way. All the bonds are exothermic. All the bonds are exothermic, or forming bonds are exothermic, isn't it? Even in life, it's the same. Making bonds is exothermic, isn't it? It makes heat, huh? Heat. Yeah. It makes heat, isn't it? Whatsoever the bond is, it makes heat. Yes? So all the bonds are somewhat exothermic, right? Whatsoever the bond is, it's sort of exothermic, yes. It has a heat. It releases the heat. You will experience it. Already have experienced the heat? I have experience, yes, of course. I have experienced the heat many times. Not almost, I'm over 30. Yeah. Yeah. Mamad? Clear. Right? So now come to this one. If the heat of reaction is negative, it is an, you two girls, listen when I'm teaching. So if the heat of reaction is negative, it is an exothermic reaction, right? It is an exothermic reaction. Exothermic reaction, right? Exothermic reaction, right? And this graph is important. These people know, right? This comes for the exams. Yeah. Yes. Right. So an exothermic reaction can be represented graphically as follows, right? So this is how you graphically draw it. Now there's a way of drawing it. There's something other than the exothermic reaction you're supposed to know. For a reaction to occur, right? For a reaction to occur, there has to have a activation energy, right? Has to have activation energy. And it's an energy that is other than the heat of reaction. Why are you crying though? You're worried about the heat of the reaction, huh? Right? So other than the heat of reaction, it has to have a activation energy as well, right? It's like the tickle that Johasa gave to the Johan when the bonds were breaking, right? Has to give a bit of a tickle for the activation, right? It's something like this. Let's say Penuja is there in the classroom, right? And Johasa comes and is telling Penuja, me Ravishka මෙන්න මෙහෙම කිව්වා මෙහෙම මේ කරනවා කිව්වා කියලා she gives some energy to Penuja, right? That's the energy, sort of an energy that you don't see but is given, right? And Penuja, what happens to Penuja? Penuja gets motivated and excited, so he goes to Ravishka to heat to release his energy, right? To release his energy. And if Penuja hits Ravishka, that's a exothermic reaction because the Penuja's energy was released. Yes. And if other way happens, if Penuja goes and gets beaten up, that's a endothermic reaction because Penuja went to hit, but instead of hitting, he was beaten up. So he absorbed it. He took the energy to himself. So that's a endothermic reaction. So both of the reaction to occur, the Yuasa had to now give the energy, right? So that is the activation energy. Whatsoever the reaction is, could be exothermic, could be endothermic, but the activation energy is a must, and it's a jump of the energy from the reactant to a higher energy level, right? It's always a jump. Yes. So now in an exothermic reaction, now come to this point. The two of the axes are there. One is the energy. The other one axis is reaction progress. Where the reaction happens, it always happens like the reaction usually happens forward. Yes, from the reactant to product usually happens the reactant to products, right? So the reactant supposed to be here and the product supposed to be in the front. Yes, product supposed to be in the front. So now let's say in two of these dotted lines, which should be the reactants? This one or this one? Let's say this is A, this is B. The reactant should be A or B. Girls in the back. The reactant should be, if this is an exothermic reaction, which has to have the greater energy in exothermic reaction, reactants or the products? Exothermic means, yeah, more energy releases. Yeah, so the reactant has more energy. Yes, so this is the energy. So this should be reactants. This should be, so this is reactants. And even in the reaction progress, the product should occur after the reactants, isn't it? Because the first is reactants, then only the products occur. Yeah. Oh, where are they? It should be always the reactant first, then the products. And if you compare the energy in an exothermic reaction, the energy of the reactant is greater and the energy of the product is low. So this is what? This is reactants. Yes, this is reactants, this is products. Understood it? That is how you decide. If this is an exothermic reaction, energy of the reactant should be more, the energy of the product should be less, right? So this is an exothermic reaction, so energy of the reactants is more. What happened? Right. Now don't look back like you will like, yeah. Now you will have like mixed signals, like she seems like winking but not. She had a trouble in the eye. I don't know, I didn't check. Numbel Vinay, I'll give you. Even that I can't remember. No, 86 or something was the highest. Balam. Yes. Right? So the reactants to products, right? Now, as I said, the activation energy is always a jump, right? Listen, the activation energy is always a jump, which means from the reactants, there comes the transitional state, and then only the products happen, right? And the jump from the reactants to this transitional state is called what? Activation energy. So for a reaction to occur, you always have to have this jump of activation energy. That is the energy that it takes to convert the reactants to the products, and at this point the reactants convert to what? Products, right? And it is the reactants convert into products at this point. That is a transition. You call it the transitional state. The energy is activation energy, right? This state is called the transitional state, where the reactants convert or change into the products. Yes, it's like a bentane. In bentane, our Mahavrugadavantya, like in the middle, half bentane, the half Mahavrugadavantya, right? So it's a transitional state. Likewise, ne? Tara metana bentane inno, metana the half Mahavrugadavantya and half bentane is there, and here is the complete Mahavrugadavantya. That is a transition, right? So this is called the transitional state, where the reactant is converting to the product, right? So this is called transitional state, right? This is called transitional state, and this is called what? Activation energy, right? This is called activation energy. And can somebody tell me where's the heat of reaction? How do you show the heat of reaction in the graph? Heat of reaction is the energy either released or absorbed. How do you show it in the graph? That's the difference of energy of products and reactants. So the energy of product is this, energy of reactant is this. So the heat of reaction, if I take it as delta H, this gap should be the heat of reaction, the energy difference between the product and the reactants. So this is what? This is the heat of reaction. Yes, that is the heat of reaction. Understood it? Up to that point? Yes? With one eye? Understood it? Nice. Online people, could you please tell me if you understood it or up to this point? Huh? Oh. Now people online, draw a sketch. Understood. Nice, good. So draw a sketch of this. Sketch එක ගහගන්න කොලයක. It's good, like it's always good to draw the whole diagram. You okay? No, okay. It's always good to draw the whole diagram because you will like get questions like that, to draw the energy diagrams of an exothermic reaction and an endothermic reaction. Past paper questions වලත් තියෙනවා. මම මේ ටික දුන්න ඒවෙත් තියෙනවා නේ. පළවෙනි පේපර් එකේ graph එකම තුන්වෙනි පේපර් එකේ තියෙනවා. ඒ කියන්නේ හදාගෙන නැහැ. ඒ කියන්නේ පළවෙනි graph එකේ වැරදියට ඇඳ නම් discussion එකේදී හැදෙන්න එපා. තුන්වෙනි පේපර් එකේත් ඒ graph එකම හැදෙයි. ඒක හදා ගන්න ඕන. improve කර ගන්න ඕන. ඔක් කළා තිබ්බේ කවුද? චමත්ද කොහෙද? චමත් තමයි ඇඳදී. චමත් ඇඳදී බොහෙම නායක්ව. මේක මෙන්න මෙහෙම දාලා ඇඳලා axis එක label කරලා තිබ්බෙත් නෑ. ඒ පොඩි miss points හදා ගන්න ඕන. එතකොට තමයි improve වෙන්නේ. ඔය paper එක වැඩක් වෙන්නේ ඔව් discussion එකත් එක්ක තමයි discussion එකේ මේ කියන්නේ mistakes හදා ගන්න ඕන. එතකොට තමයි improve වෙන්නේ. නැත්තම් තේරුමක් වෙන්නේ නැහැ. Right, finish? Come to the next one. Accordingly, right, if the energy of the reactant is greater than the energy of the products, the reaction is called what? Accordingly, if the energy of the reactant is greater than the energy of the products, the reaction is called exothermic reaction. Yes, exothermic reaction. So it's a exothermic reaction. Exothermic reaction. It's exothermic reaction, right? So that's exothermic reaction. Now the next thing is endothermic reaction, right? So in an endothermic reaction, what should happen? The energy is absorbed, right? The energy is absorbed. So if the energy is absorbed, how would it feel to the environment? It should be feel cool, right? It should feel like a cool. So now this is a glass of water, and if I put a bit of glucose into it, how, depending on the reaction, the dissolving glucose in water should feel cool because Anna, good question. Monada cool වෙන්නේ? Water the cool වෙන්නේ? Cool වෙන්නේ water the? It's actually the environment gets cool because the energy is absorbed from the environment to the system. Yeah. So the environment is getting cool. Huh? Water වලට තමයි absorb කරන්නේ, but energy was absorbed from the environment. So the environment is losing energy or the heat. So environment gets cool, and you are the environment, right? That is the next theory we are going to discuss, right? This is a system. The glass of water is a system. Huh? What? Eh? Oh. ඒ කට නෙමෙයි. ඉතින් දැන් ඒ කියන්නේ කටට තමයි සෙන්ස් වෙන්නේ. කියන්නේ දැන් මේකෙදි දෙකක් තියෙනවා. එකක් තමයි සිස්ටම් එක. One thing is a system. So in this case, the water glass is the system. Everything else is the environment, right? Everything else is the environment. So when I apply the glucose to the water, the reaction occurs inside the system, and the energy is absorbed from the environment. So the internal energy of the mixture or the system is increased because it absorbs the energy from the environment, right? The internal energy is increased, but you don't see it. It's the internal energy, as we discussed. It's the internal energy. Internal energy is increased. You don't see it though, but you can feel that the heat was taken from the environment. You can feel it, right? That you can feel it because you are the observer. Always the observer feels, right? And make a කටර දාගත්තාම පස්සේ the observer becomes the system. Yeah, the observer becomes the system itself. Yes. And so you feel the loss of energy from the environment, right? ඔයාලා දැනෙන්නේ අර environment එකෙන් lost වෙච්ච energy එක තමයි ඔයාලා දැනෙන්නේ, right? So I'm going to do a experiment. Can someone come? Now everybody want to see you. Yes, come to the camera. No, I was kidding. Come. I go off kar. Camera go off kar. Come. Right. So guys, this is the most annoying person in the class. Penuja, come. He's the one who always asking questions. I turn to this direction. Yeah, face phone see or kalui. Yeah, you don't emit the light. So you tell me what you feel, huh? Right? You tell me what you feel. So I'm going to add glucose to the water. So the water glass was a bit hot at the beginning. Supposed to get cold. Do you feel the cold? Not yet? What do you feel now? You feel?
Cold.
cold. So what has happened now? Now this is the system, the glass of water with glucose is a system, and when the reaction occurs, the energy was absorbed from the environment, and you are the environment, and the glass of water with glucose is the system. So the system absorbed energy from the environment, and you sense the loss of energy from the environment. That is the sensation, the loss of energy from the environment is the feeling of the cold. Yeah, thank you. No, you take it. That's okay. Gun. Hey. Right. So now, similarly, if the energy of the reactants is less than the energy of the products, right? Energy of the reactants is less than the energy of the product. Yes. The reaction is called what? Now the energy of the reactants is less than the energy of the, it should be other way around. I think I have here. Similarly, if the energy of the product is less than the, it's correct, right? The energy of a reactant is less. Yeah, correct. This is correct. Good. So similarly, energy of the reactant is less than the energy of the product. So the energy of the reactant is less. The energy of the product is more. So it's a reaction is called endothermic reaction, right? It's an endothermic reaction. So heat is absorbed when the reactants react and the products are formed, right? So when the P and Q are reacting, heat is absorbed and the product RS is formed, right? So the heat of reaction is equal to energy of products minus energy of reactants. Shall I write it this way now then? Heat, we don't care. Let's say the energy of P and Q is 5 joules and the energy of product is 10 joules. So now the energy has increased, right? So the heat of energy should be how much? 10 minus 5, that is plus 5 joules, right? So if the heat of reaction is positive, it is a, so the heat of reaction, what do you get here now? If I apply the values, energy of the product is 10 joules minus energy of the reactant is 5 joules, and the answer is plus 5, right? You don't have to write it plus, but it's a plus 5, isn't it? So if the heat of reaction is positive, means the value is a positive value, it is a endothermic reaction. It is an endothermic reaction. Thermic, right? It's an endothermic reaction. And now we have to draw the graph, right? So how do you draw the graph? Now you tell me which is reactants, which is products. Which one is reactants? This one. This is reactants. This is products, because the product has more energy, reactants has less energy. So this is reactants. And this is products. And they are supposed to be sort of an energy to initiate the reaction. What is the energy that it takes to initiate the reaction? Activation energy, and it's always a jump from the reactants to which state? To the transitional state. It's always a jump from the reactants to the transitional state. So the jump goes like this, right? So now tell me the activation energy. What is the activation energy? Which gap is it? The gap between reactants and the transitional state, right? That is the gap between transitional state and the reactants. So this is activation energy. We label it EA, activation energy, right? And this is what? This is the transitional state. Transitional state. And this is activation energy. Activation energy. Right, this is activation energy. And the heat of reaction is the energy gap between the products and the reactants, right? Energy gap between the products and the reactants. Then glucose rahana isara. Maybe the nerve cells damaged. Nerve cell aged. Cell aging. You don't feel the same. Yeah, taste difference is there. Right? Take a note. වෙනස් නේ රහ. වෙනස් රහ වෙනස්. ක්වොලිටි එක පොඩ්ඩක් අඩු කරලා. ඉස්සර ඔහම නෑ හරි රහයි. පිස්සු වෙන එකවනේ ග්ලූකෝස් එක හම්බුනා මොකද? රහ වෙනස්. Right? Do you understand this part now? Yes. And you're supposed to remember the energy graph of exothermic and both endothermic. Yes. මේක එනවා අඳින්න එනවා. ඒකේ වැදගත්ම දෙක තමයි මෙන්න මේ දෙන්නව මතක තියාගන්න. ඒ කියන්නේ ගොඩක් කරලා අමතක කරන්න. ඒක වැදගත්ම දෙක නෙමෙයි. Most of the time you forget the accesses, energy and reaction progress. ඕක තමයි අමතක වෙන්නේ. අනිත් ඒවා ඔක්කොම මතකයි. access දෙක මතක නැහැ. හරි. ඒ දෙක මතක තියාගන්න හොඳට. Energy and reaction progress. Yes. Right, come to this one. Transfer of energy between the system and the environment. Now we discuss something in like the environment and the system, right? We discuss something environment and the system, and when it comes to this one, the glass of glucose water, this was the system, yeah, this was the system, and everything around it is the environment, right? Is the environment. So now in a reaction, the energy is always transferring from the system to the environment and from the environment to the system as well. The energy exchange is always there from the system to the environment and from the environment to the system. Now think like it's a good thing, it's an easy way to remember. You think yourself as the system. Think you are the system. So you are the glass of water, like the Bruce Lee says, be like water, right? So you are the glass of water now, yeah? So you are the system, and everything else is what? Is the environment, right? Everything else is environment. And usually what happens is, sometimes you release the energy to the environment, which means the system releases energy to the environment. And you sometimes absorb the energy from the environment as well. That means the system absorbs the energy from the environment. That happens. The energy exchange happens, right? The energy exchange happens between the environment and the system. Yes? Understood? That is simple, right? And there are two ways that the energy exchange from the system to environment and from the environment to system. There are two ways that the energy exchange. One is as heat. Yes, one is as heat. The other is the work done. Like there are two ways the energy exchange. One is the heat. The other thing is work done. Right? I'll take an example like this. Harid. Where's that circle now here? Right. I'll take an example like this. Now listen to this. Right. So let's say this is a piston. Like I'm explaining in this in a different way. I don't know how actually this is not the actual way of piston working, but I'm taking just an example. So let's say this is a piston, right? Now this is a chamber and there's some sort of petrol or something in it, let's say. And the petrol is combusting inside, or let's say methane. Methane is combusting inside and produces carbon dioxide plus water, and the energy is released, right? The energy is released, right? The energy is released when the combustion occurs, right? So inside the piston, the combustion occurred and the energy was released. One way the energy was released is the heat, right? One way the energy release is heat. So the piston is getting heated, right? Because of the energy release, the fraction of the energy release converts into heat, so the piston is heating up, right? And the rest of the energy is lifting the piston up. That is the work done, right? That is the work done. So the energy release is, one is the heat, the mc theta, the other one is the work done. Yes. So what happens here is the piston is lifted up. Yeah, the piston is lifted up, right? Right. So the energy released was converted. One is the heat, mc theta, and the other thing is the work done, right? The work done, F into D, right? F into D. Hands up those who understood it. The energy release was converted to heat, the mc theta, and the work done. So which energy was this release? Which energy was this? This was the internal energy. It was the internal energy. You can't calculate the internal energy anywhere, like using any of the equations. But in this reaction, the internal energy was released. Now you can calculate it. Can you? You can actually. How? You calculate the heat release using mc theta, and you calculate the work done by Fd. So this mc theta and Fd together is the internal energy. So you can calculate the internal energy. Do you understand that? You can calculate the internal energy, isn't it? You calculate it using the work done and the heat release, right? So that is why we, from the very beginning, I told you that the energy or the energy is exchanged between the environment and the system in two ways. One is work done and the heat. Yes. So the piston is the system, right? Or the methane and the whole thing is the system, right? And when the reaction occurs, the heat is released to the environment and the piston is lifted to the environment, right? So the work is done to the environment by the piston, right? By the piston. So the energy release now we can calculate using the heat and the work done, and that energy release is also the internal energy of what? Of the piston. And if we go deeper, it is actually the internal energy of the methane, isn't it? It is the internal energy of the methane. But if we took it as if we took the piston as the system, it is the internal energy of the piston, right? If we go deeper, it was the internal energy of the methane actually. But if we took the piston as the whole system, so it's the internal energy of the piston now. Yes. So the internal energy of the piston we calculated using what? The work done and the heat released. Hands up those who understood it. Huh? Then why did you I asked like hands up if you understood it. They said now Therunne. I said Therunne. I heard it like Therunne. Right? You understood it? Online people, you understood it? Yeah? So the energy exchange, the energy released by the system to the environment, we can calculate it using the work done and the heat release, right? I will tell how, right? එතකොට guys, did you understood or not? Malshi, Shiny, Sadesh, Rostel, yeah, hopefully understood or not? No, good, right? Yeah, one, yes, some yes. Now this is the thing, right? So I'm gonna like, this is the piston, how the piston works, right? So the piston is the system and the reaction occurs inside the piston, right? And the energy is released, yeah, the energy is released, right? So the energy of the piston or the energy of the system is released, yes. And in the beginning I told you that when there are two ways the system and the environment exchange the energy. What are the two ways? Work done and the heat. Work and heat are the two ways the energy is exchanged. So inside the piston the reaction occurred and the internal energy was released, and that the piston is the system. So the internal energy that is released is exchanged with the environment as heat and work done. Yes, the heat and work done. So internal energy of the piston now we can calculate as the heat release and the work done, right? Yeah. Now I will explain it another way, right? This is another way of explaining it. Let's say who goes to the gym? Johan goes to the gym, right? Let's say Johan goes to the gym, right? Now when Johan goes to the gym, now this is Johan with the big muscles, yeah? Right. If someone is imagining how Johan looks, yeah? Now Johan goes to the gym, right? And let's say he ate an apple in the morning. You ate apple in the morning. So the apple he ate becomes his internal energy. Yes, his internal energy is now produced. The internal energy is now there in your stomach. Now you can use it. Yes. So the internal energy is there. Let's say 100 joules of internal energy is there in his stomach. Yes. That's the energy of the apple. And now he goes to the gym. Now he is the system, right? I told you that think yourself as a system. That is easy. Yeah. So now Johan is the system. Yes. And he is lifting a dumbbell. Right. So this is a dumbbell. He is lifting a dumbbell. Right. He is lifting a dumbbell. So when he is lifting the dumbbell, he uses his which energy? The internal energy he took. Yes, the apple. Yeah. He is using his internal energy to lift, right? So his internal energy is now converted into work. He is lifting the dumbbell, so it's the work done. Let's say it's 30 joules or something. The work done is 30 joules. That 30 joules was taken from where? From the system, from the internal energy. Yes. And what happens when he's lifting the dumbbells? He's sweating. Heat is released. Yes. So the heat is released. Yeah. The heat is released. He's sweating. So this is also energy, isn't it? Now this heat energy, let's say was 70 joules. Now what happened to this internal energy? Was converted into the work done and the heat release. Yeah. So it was the apple he ate. So the internal energy of the system was transferred to the environment in two ways. What are the two ways? The work done, the dumbbell lift, and the heat release. Yeah. So even the same in a piston. So you are like a machine. Yeah, you are like a piston. So the energy is produced inside a piston, and the energy is released to the environment in two ways. One is the heat and the lift of the piston, which is the work done, right? So that's what happens there. Now you understood it, Malshi? So this is internal energy of the system. This is the work done. This is the heat released. Yes. So the internal energy is equal to the work done and the heat released. Yes. So we can write it as an equation. Yeah. We can write it as an equation. How? I'll take the internal energy as delta E. Now this is something you supposed to understand. This is delta E, the difference of internal energy, right? So you ate an apple, we use the energy of the apple, right? Not the whole energy yourself, isn't it? You didn't use the whole energy of yourself, right? If you use the whole energy of yourself after doing a dumbbell lift, you're collapsed. So you use the fraction of your internal energy, right? Even in a combustion, you use the fraction of a internal energy, not the whole thing. You can't use the whole thing ever. You only use a fraction of. Even in every reaction, you only use a fraction of the internal energy, right? So now here, Johann was using a fraction of the internal energy, right? That's 100 joules. His internal energy is more than that. He only used 100 joules. So the 100 joules of system was changed or transferred, right? To where? To the where? Environment. This was transferred from the internal energy, was transferred from the system to the environment. How? As the work done, we call it delta Q. Sorry, the heat release, we call it the delta Q. This is the heat release plus the work done. Get it? So we can calculate this internal energy using these two things. What are these two things? The heat release and the work done. We can't calculate this when it's inside of you, right? We can't calculate the energy of apple Johann eat when it's inside your body, no? But we can calculate it how? With the work done and the heat release. So how do you calculate the work done? How do you calculate the work done? That is FD. And how do you calculate the heat released? That is MC theta. Yes. So using these two, you can calculate the internal energy, right? You can calculate the internal energy. Hands up those who understood it. So you can calculate the internal energy by the work done and the heat release. If the energy was released, yes, if the energy was released, is it always releasing the energy? No, sometimes the energy is absorbed as well. Yeah. So if the energy absorbs, now the heat is taken to the system and the work is done to the system. Now in this case we discuss, this was releasing the energy from the system to the environment. Right? දැන් අපි glucose dissolve වෙනවා වගේ කරනවා. එතකොට මොකද්ද වෙන්නේ? heat එක environment එකෙන් system එකට absorb කරගන්නවා. ඒතර internal energy එක වැඩි වෙනවා නේ. මේ කේස් එකේදී මොකද්ද වෙන්නේ? system එකෙන් energy එක එළියට release වෙනවා. ඒතර එයාගේ internal energy එක අඩු වෙනවා. ගොඩක් heat එක energy එක release කරන ඒවා තමයි වැඩිපුර තියෙන්නේ. වැඩිපුර තියෙන කියන්නේ අපි වැඩිපුර කතා කරන්නේ heat එක, ඒ කියන්නේ energy එක release කරන ඒවා. ඇයි අපිට ඕන energy එක release කරන ඒවා නේ. ඔව් අපි පාවිච්චි කරන්නේ එනර්ජි එකනේ නේ fuel fossil fuels විදියට හරි මොනවාට හරි අපි bio fuels හරි පාවිච්චි කරන්නේ එනර්ජි එක රිලීස් කරන ඒවා. එහෙනම් අපි වැඩිපුර කතා කරන්නේ එනර්ජි එක රිලීස් වෙන පැත්තේ තියෙන ඒවා, right? And do you understand this equation? Yeah. But this equation can happen in two ways. Hello. Yeah. Good afternoon. Right? So you understood this? Yeah. So the internal energy sometimes is released and the internal energy sometimes is absorbed. So in cases like if the internal energy is released, think yourself as the system, as I said earlier, think yourself as the system. So if the internal energy is released, your energy is taken out, yeah, so it becomes minus to you, right? It becomes minus to you. So the if the internal energy is released, the delta Q is always minus, right? Delta Q is minus because it is reduced from you, yeah. And if the internal energy is released, the delta W is also minus. If the energy is absorbed, yeah, energy is absorbed to the internal energy, that means the internal energy should supposed to be increasing, yes, internal energy is supposed to be increasing. If the energy is absorbed or the heat is absorbed to you, the delta Q is plus because it's adding to you, isn't it? And the work is done to you, that means the work is adding to you, which means delta W is plus, right? So in some cases the delta Q is minus and the delta W is minus, and in some cases the delta Q is plus and the delta W is also plus. When the energy releases from the system, delta Q is, when the energy is released from the system, delta Q is minus and the delta W is minus. When the energy is absorbed to the system, delta Q is plus, and when the work done to the system, delta W is plus, right? So it happens releasing and absorbing the both way, yeah. So because the energy is, you know, transferred between the environment and system, sometimes the system releases the energy and sometimes the system absorbs the energy. So we can calculate this transfer using the heat and the work done, right? Right. So that is the basic. Now come to the theory. So the above internal energy is transferred, the energy released or the absorbed, right, is transferred between the system and the environment, right? The above internal energy is transferred between the system and the environment. There are two ways in which energy is transferred. What are the two ways? Heat and the work done, right? The heat and the work done. Hands up those who understood up to now? Yeah, good. So the online people, did you understand up to now? Basics? Yes? Yes, nice, right. Right. So now you have to identify the system, environment and the frame out of the system as well. Now three of the things are there to understand, but system, environment and boundary, right? So as I said, system, right? I told you to think yourself as a system always. And the system is what, if I define it, the system is the part of the space or the universe that we observe and examine for study, right? So the system is what? the part of the space that we observe, right? So if you are taking yourself, that is the part of in the space that we observe or that we examine, that we think of. So if you are taking something to examine or to observe, that becomes the system. So if I started to examine this glucose glass of water, this becomes the system. Yes. So now environment, all the remaining areas of the universe excluding the system are called the environment. So except for the system, everything else is what? Is the environment. So yourself, if compared to the glucose water, is environment. Everything is environment, right? And the boundary is the border that separates the system and the environment. Now in this case, the glass cover, separates the environment and the system, right? So that is the boundary. Yes. So three of the things are there. What are three of things? One is the system, that is the part of the universe that we observe and examine, and the second thing is environment, that is everything except for the system, and the boundary is the margin that separates the environment and the, right? Simple as that. So now this is the system. Everything around is environment, and this white part is what? That is the boundary. Yes, this white part is the boundary. Yes, right. Right. So considering the exchange of energy and the matter, now I will come to this part. Before that, come to this part. Not that part. Not that part. Not that part. Not that part. No. It's there up somewhere. I can't remember where now. Doesn't matter. I will come to this. Right. Now think of this one. Now tell me, with the theory knowledge that you know. So there's system, there's environment, right? What do you call the system plus environment? If you know, if you learned it already, don't tell. Okay. Oh, this guy. Okay. So what is? Huh? You don't know. If you say so, I believe it. Yes. So now tell me, environment and system together. What do you call it? Huh? Open Gangnam style. Open system. No. The system and the environment together. Yes. No. Don't read the tube until what the answers. The system and environment together, because system is something that you observe and examine about, and everything else is environment, isn't it? So that everything else plus the system is what? Is everything. Is the universe, isn't it? Yeah, everything is universe, isn't it? So the system is the part that you observe, and everything else except the system is environment. So the everything else except the environment, everything else except the system and the system together is, yeah, everything that is universe. Yes. So you can tell this what? The system plus environment, yes, is what? Is universe. Yes. The system plus environment is universe. Yes. So now tell me this. I am trying to prove one of the laws. One of the laws of energy. Yeah. So now tell me the answer for this. right? So now you are the system, yes, and the surrounding is the environment. So now we are releasing 10 joules to the surrounding or the environment, yes. So you are losing 10 joules, that is minus 10, and the environment is absorbing or adding 10 joules, that is plus 10, yes. So what is the energy difference of the system? Now I said ඔයා 10 joules release කරනවා, environment එක 10 joules ගන්නවා. Now what is the energy difference of the system? Is it plus 10 or minus 10? System, because system lost energy, 10 joules lost to now, minus 10 because you lost 10 joules. And what is the energy difference of the environment? Plus 10. එයාට 10 add වුණා. And what is the energy difference of the universe? 20. It's okay, you don't have to confirm, huh?
0.
So the system released 10 joules, that is minus 10. Environment added 10 joules, that is plus 10. Yeah, so the energy difference of the universe is what? Is 0. So that's a law, isn't it? Because the conservation of energy says what?
When you lose something, you gain something. When you gain something, you lose something, right? That's
Say it again. When you gain something?
You lose something.
Yeah.
When you gain something,
lose something.
I don't know, you ask her. Okay, what? Yeah, so the law of energy, conservation of energy says what? Energy cannot be destroyed or created, yeah? Energy cannot be destroyed or created. The energy of the universe is always constant, yes? Energy of the universe is constant. If it is 100, that means it never becomes 101 or 1990, yes? Always the energy inside is converting from one sort of energy to another sort of energy, yes? So always the energy, if I consider some sort of a thing as the system, so sometimes the system releases the energy to the environment and sometimes the system absorbs the energy from the environment. So the energy is also always transferring from where to where? From the system and the environment, right? Energy is always transferring between the system and the environment. So system is something when we observe, right? System is something that we observe or we examine about. So sometimes the system absorbs the energy, sometimes the system releases the energy, and sometimes the environment absorbs the energy and sometimes the environment releases the energy. That is what happens, right? But the energy of the universe remains constant. So there is no energy exchange or like energy difference in the universe. Always the energy difference is there in the system and the environment. The energy difference of the universe is 0. So this was one of the past paper MCQs. It was said like system loses this much of energy, the environment gains this much of energy, and the question of what is the energy difference of the universe. So it's 0, yeah, because the energy of the universe is a constant. Yeah, that is the law of conservation of energy, right? Nice theories, ne? Bit of a brainstorming theories, and these are like most of the basic science theories are, you know, those are conceptual, like those are concepts. So you have to think it that way to understand it. Yeah. So you have to be like a nerd. Usually usually no, I won't say the nerds, because like you have to imagine things like a story. like a story, like Harry Potter or something. Nee? You have to imagine things, so you will understand it. That is how the science works usually. You have to have a better imagination to have a greater understanding of the science, or the how the the physics and everything work, physics, chemistry and biology, everything work. You have to imagine things, so you will start understanding. Right, so come to this one. Considering the exchange of energy and matter between the system and the environment, there are three types of systems can be distinguished, right? Now listen, so depending on the two things, one is the what? The exchange of matter and the exchange of energy, right? Depending on the exchange of matter and energy, there are three types of systems. What are the three types of systems? One is open system. The other thing is not the open Gangnam style, the open system, right? So open system is one. The other thing is closed system, and the last one is isolated system, right? So there are three systems: open systems, closed systems, and the isolated system, right? So let's define the systems. Now, what is an open system? So as the title say, the depending on the exchange of matter and energy between the environment and the system. So what is an open system? That means the open system means the energy and the matter are both exchanged between the environment and the system, because it's open. Yeah, anything can come, anything can go. It's an open system, right? So in an open system, energy is okay to exchange. Yeah, so energy is okay to exchange, and the matter is okay to exchange as well. Yes. And in a closed system, what is a closed system? In the like if we consider the energy and the matter, out of two, only one can exchange, the other can not, right? So it has limits, like the boundaries are there. Only energy is allowed, matter not allowed. Yes. So they don't allow the closed system don't allow the matter no, the energy fine. So the energy no, but the matter, oh I'm sorry, this is the other way. Energy can, right? Energy okay, but the matter no, right? And when it comes to isolated system, right? When it comes to isolated system, it's right? When it comes to isolated system, the energy and matter both are not allowed, right? The energy and matter both are not allowed, right? When it comes to isolated system, energy is not allowed, the matter is also not allowed. So when I'm asking the questions after the lesson finish, if you couldn't answer it, I'm going to hang you in the, right? Listen, right? So what is the first system? The open system. The energy and matter both are okay to exchange. Yes? So now can you come up with an example? Yeah, like the glass of water, which is open. And it's better if I take the coffee cup. Yeah, the better example is a coffee cup. An open coffee cup. What happens to an open coffee cup? Open coffee cup, the energy is transferred to the environment. So it's open for the energy. And even the particles, the matter, with the convection, it goes out, isn't it? With the convection, it goes out. So the matter is also exchanged. Sometimes the fly might come inside as well. So the matter exchange. Even the wind can come inside. So the energy exchange. So in an open system like a open coffee cup, the heat or the energy and the matter both are exchanging. Yes. And when it comes to a closed system, only energy is exchanged, but the matter cannot. it's like if you close the system, right? It's like if you close the system, now what happens? If this is a coffee cup, the convection can't occur. So the matter does not exchange here, but the heat or the energy is always going outside, isn't it? So the energy is exchanged, but the matter isn't. It is called a closed system. So if it is an isolated system, both the matter and energy cannot exchange. Yeah, like a thermo flask. So if it is a thermo flask, the energy is not allowed to exchange and the matter is also not allowed to exchange. So a good example, like a better example for a isolated system is what? A thermo flask. Yes. Right. Come to the open system. Now online people, did you understand three types of the systems? Open, closed, isolated, depending on the exchange of matter and matter and energy. Yes, good. So come to the open system, right? A system that exchange energy and matter with the environment is called an open system. An example is what? Open coffee cup. An open coffee cup. See, the matter is released or exchanged, the energy is also exchanging. Next one, the closed system. Yeah, systems that only exchange energy with the environment are called the closed systems. The energy is exchanged, but the matter is not, right? The matter is not. What is a good example? A closed coffee cup. A closed coffee cup is a closed system. An isolated system that cannot exchange energy or matter with their surrounding are called isolated systems. Example is a thermos flask. How do you fill a flask? Fill SK, is it? Thermos flask. Thermos flask. Yes? Yeah. Right. Now come to this one. It was discussed above that the transfer of energy between a system and its surrounding occurs as heat and work. Right? We discussed that part. The exchange of energy occurs as heat and as work. In this, heat can be defined as the flow of energy caused by temperature difference. We already know that. We discussed it under the heat physics. Yeah. Right. First one, the change in the thermal energy occurring in the system, amount of thermal energy can be calculated by MC theta. If you want to calculate the amount of heat transferred, you can use MC theta. And the change in performance or the work, right? Change in work, write it down, work as well, of the system. Work is the transfer of energy from one object to another to move it in a certain direction. We can calculate it using FD, right? FD. And there's another way of calculating it, right? Now we discussed this part, right? Like piston is lifting because of the internal energy released. Yeah. So FD is one way of calculating the work done, and there is another way. This is the new formula you are learning. That is PV. W equals PV. PV is the pressure into volume difference. Now there is a volume difference that happens, right? When the piston is lifting up from there to here, the volume is increasing, isn't it? The volume is increasing or the volume is changing, isn't it? And that happens because of the pressure. Yeah, because of the pressure the volume is changed, right? So now if I multiply the pressure by the volume, there's something that you get. What is the thing that you get? Yeah, so how do you find it? The pressure is what? Pressure is force over area, and the volume is cross-sectional area to the height or the displacement, right? So what happens now? Area to area cancels out, and what do you get? F into D. Now F into D is what? Is the work, isn't it? Is the work. So PV, pressure into volume, is also equal to what? The work done. The pressure into volume is also equal to work done. Understood it? So this is a new formula you are learning. Work equals pressure into volume. Yeah, that's a new one. Work equals pressure into volume. And this equation ඇවිල්ලම නැහැ. exams වල නම් ඇවිල්ලම නැහැ. ඒත් දන්නේ. ඔයගොල්ලෝ මේගොල්ලන්ට ඒත් දන්නේ නැහැ. The 25 people ආවතින් ගොඩ තමයි. හරි එන්න පුළුවන්. Right. So this is a new equation na. Put a star mark or highlight it, do anything. Huh? Theory ati? Right, we'll finish it. Now we have 5 minutes to go. Right. මේ අපි කතා කරපු ටික තියෙන්නේ දැන් මේ. නේ? අපි කතා කරපු ටිකමයි තියෙන්නේ. ආපහු මේ ඒ කියන්නේ මේ දැන් මේ ඩිස්කස් කරපු තියරි ටිකමයි තියෙන්නේ. You just only have to go through back it again. That's all. අර දැන් මේකේ ප්‍රෙෂර් එක නැහැ. This is zero pressure. You just only have to අර memorize කරගන්නවා වගේක් තියෙන්නේ දැන් අපෝ. Right. Right. Listen. The sum of listen. The sum of the above amount of thermal energy and the above amount of work can be called the internal energy of the system. You understand that, right? The above amount of thermal energy and the work done is the internal energy of the system. एक internal energy के नहीं right? So we can write it as what? Delta E, the internal energy equals delta Q plus delta W, right? So delta E is what? Internal energy change, and the delta Q is thermal energy difference, and the delta W is work difference. So you have to know that's like the difference. නේ අර අපි කතා කරේ කියන්නේ යොහාන්ගේ internal energy එකේ ඔක්කොම නෙමෙයි difference එකක් වෙන්නේ. කියන්නේ internal energy එකෙන් කොටසක් transfer වෙනවා work done එකට, කොටසක් heat එක විදියට. ඒතර ඒක delta difference. ඒ කියන්නේ internal energy එකකින් fraction එකක් තමයි එළියට එන්නේ. එතකොට environment එකෙත් increase වෙන්නේ කොටසයි. heat එක විදියට environment එකට හම්බෙන්නේ කොටසයි. මොකද environment එකෙත් කොටසක් තියෙනවා. already තියෙනවනේ heat එකක් නේ. එතකොට ඒ තියෙන amount එක තමයි වැඩි වෙන්නේ. ඒකයි අපි delta කියලා ගන්න. difference කියලා ගන්න එකයි. තිබ්බර වඩා පොඩ්ඩක් වැඩි වෙනවා හරි අඩු වෙනවා. That's the difference always. Yes. Right. So if the amount of internal energy produced by the combustion of fuel in a piston is considered to be delta E, also symbolized as delta U sometimes, the internal energy converted into the heat energy of the system is simple Q. Heat energy කියලා අපි ගන්නේ මොකද්ද? Simple Q. And the work done in a lifting the piston is W. Work done කියලා අපි ගන්නේ W. We can write what? Delta E equals mc theta plus p delta v. It's the same equation. Delta E equals delta QW delta W. එතකොට අපි delta Q එක measure කරනවා මොනවා විදියටද? mc theta විදියට. delta W එක measure කරනවා p delta v විදියට. Right. So when මේක අර අපි දැන් කතා කරපු අනිත් එක, when a person eats, his internal energy is increased by an amount of delta E. Now this is Johan in our example. Yeah, he's lifting a dumbbell. Yes. So energy is increased by an amount of delta E. Some of that increased internal energy is used to do work, and the rest of the internal energy produced is dissipated as heat. නේ කොටසක් work done අනිත් එක heat released. Yes. So this is again the same thing. What? The internal energy delta E is released as heat and the work done. So you can measure it using mc theta and fd, the work done. And now this is important. When considering delta Q and delta W, work transfer can be divided into 4 types, right? One is heat transfer to the system. Heat transfer in a system එකනම් we take the delta Q as plus. This is important. Example, a piece of ice melting. හරි. එතකොට delta Q උරා ගන්න ඕනේ, heat එක උරාගෙන නේ melt වෙන්නේ. එතකොට delta Q plus. The other thing is heat transfers to the environment. Environment එකට heat එක යනවා. එතකොට delta Q minus. ඒ කියන්නේ heat ඒ කියන්නේ system එක ඔයා කියලා ගන්න. ඔයාගෙන් එළියට යනවා නම් minus. නැත්නම් system එකෙන් එළියට යනවා නම් minus. System එකට එනවා නම් plus. For example, leaving a cup of hot tea exposed to the environment, what happens? The heat is releasing to the environment from the cup of tea, which is the system. Performing work on the system, that is delta W plus, right? That is delta W plus. Example, blowing up a balloon. When you are blowing up a balloon, the internal energy is increasing. I work done when the balloon negative. The other thing is performing a task on the environment. Example, releasing air from the balloon. එතකොට work done වෙන්නේ environment එකට. එතකොට delta W minus, right? Right. So you have a bit of a homework to do. Yeah. So try doing these homeworks at home. That's why it's called homework, right? Yeah. So bit of a questions are there. So try doing these questions at home, and we will discuss a new part the next week. So we even discuss this part as well, law of conservation of energy, delta E system, delta E environment plus delta E universe, right? We discuss this part as well. So we'll start from a new part, do the homework, and I'll see you the next week. Yeah. Adios. Listen to the car. තාත්තා අහනවා දකුණු ගත්තද කියලා මොකක්ද දන්නේ තාත්තා ඈ Yeah, open system. No boundaries, huh? Closed system. You can only body look your bed. Jen, tell someone to come. What?